Hello everyone. In our previous video, we talked about the free response of single degree of freedom undamped systems, which means the friction is not affecting the system. So you can actually use the conservation of energy to find the equation of motion of the system. But in this second video, I will talk about the free response of single degree of freedom, but damped system, so friction is part of the system. Let's look at some examples. So what causes, what will be the effect of damping on the free vibrations? We designed a 2 degree of freedom system, but we locked the second card here, so this will turn to be just a 1 degree of freedom system. So for that, which is sliding on a card, if you displace the card in the video, once you displace the card to a certain point and release, the slider will move back and forth until it stops due to the friction. And actually, the same phenomena exists for the rotational system as well. If you rotate the rotational disc and then release, it will stop after a couple of seconds. And true for the flexible beam as well. If you displace or apply a tip load to the cantilever beam and then release the cantilever beam, it will oscillate back and forth or up and down, and it will stop because of the friction effect, as seen in the video here. Now, let's continue with the theory. In my sketch, I specifically included the damping constant, which represents the friction in the system. If you move the card to the right to get to the equation of motion, if you move the card to the right, then you're stretching the spring, and the spring, as in this previous example, is a fixed to the wall and free, which is attached to the slider. So if you move the slider to the right by x displacement, there will be two opposing forces. One due to the spring force, which is k times x. That means spring forces are proportional with the displacement. That also means that the spring will affect the displacement, while the friction force is also opposing and to the left because the cart was moving to the right. It will be c times x dot. That also means that the damping force is affecting the speed, which is proportional to the speed. And here c is the damping constant of the system. Because in our sketch to the right is shown to be positive, all the forces pointing to the left will be negative. Let's apply Newton's laws of motion. So all the opposing forces which are negative should be equal to mass times acceleration. Remember what we said before? When you write the differential equation, you must start with the highest derivative term and collect like the terms in a descending order, and the input should be on the right side. This system does not have any external force. That's why the right side of the equation is 0. When you look at this equation from the mathematic perspective, what I see is we have a linear, because mass is a number, damping constant is a number, stiffness is a number. So this is a second order linear, but also a homogeneous differential equation. But physically, what I understand is we have a mass spring system, but system is free. So you're probably just introducing initial displacement or initial velocity. If you try to get rid of the highest derivative coefficient, which is m here, the equation can be written as x double dot plus c over mx dot plus k over m, which is equal to 0. To be able to solve the second order homogeneous differential equation, you need to know the system parameters such as stiffness, such as mass, and the damping constant. You must know these three parameters, otherwise you cannot solve the problem. But this equation can also be written in terms of zeta damping ratio and natural frequency. So when I write the equation using zeta and omega n form, which are the same equations, the unknowns or the parameters that must be known prior to solving the differential equation is zeta and omega n. So we dropped the system parameters from 3 to 2 using this form. But if you make an analogy, then the same terms should have the same coefficient. C over m should be equal to 2 zeta omega n, and k over m should be equal to just omega n squared. Let's look at the terms. So omega n is the natural frequency, which is square root of k over m. Zeta is the damping ratio, and damped frequency is omega n times square root of 1 minus zeta squared. Let's continue. Continuing with the most general form of a second order vibratory system equations, We did that before. We start with the trivial solution, take the derivatives, and then plug those back into the original equation and factor out by c to the e RT, and in the brackets we have our auxiliary equation must be equal to 0. The product of two functions is equal to 0, but we already know exponential function cannot be equal to 0. That gives us only one option to make the product 0. So our auxiliary equation is second order, then it means we will have two roots. So you can apply quadratic formula to find the roots of the equation in terms of zeta and omega n. So these are our roots. But then if in a second order polynomial, the roots can be real, the roots can be double, or roots can be complex numbers. So we have three cases. If zeta is less than 1, the square root will be less than 1. So this equation will be equal to negative zeta omega n. You're going to reverse the order here and include just the complex component next to it. So I have negative zeta omega n plus or minus in square root of 1 minus zeta squared times I. Negative zeta n will be your real component and your complex component will be the square root here. And the function should be e to the alpha t multiplied by a cosine beta t plus b times sine beta t. If you have double roots, then it means zeta is equal to 1. If zeta is equal to 1, this term will be cancelled out. Both of your roots will be at negative zeta times omega n. Then the solution to the problem will be c1 times e to the rt plus c2t times e to the rt. If zeta is greater than 1, then you will have the two distinct real roots because you will have two different numbers here. I have negative zeta omega n plus or minus omega n times zeta squared minus 1, and that will be the solution to the problem. Okay, let's just look at only one case. If zeta is less than 1, how we find the constants of the system or the coefficients. So again, if zeta is less than 1, you will have complex poles. And you know the real and the imaginary parts. If you plug those into the solution, it should be e to the alpha t in brackets a cosine beta t plus b times sine beta t. And knowing what alpha and beta in terms of zeta and omega n, you will get to this equation here. Assume that we have initial conditions already known. The initial displacement is x sub 0 and the initial velocity is x dot sub 0. From here, if you plug in 0 for time, this term e to the 0 will be 1. Sine 0 will be cancelled out. That only gives you, and cosine 0 will be 1. That will only give you a. So the initial position will be equal to a. So or a will be just equal to the initial position. The next thing, let's take the derivative, the product. So you have to apply product rule, you have to apply chain rule to find the derivative of this equation. Let's start with the product rule. You take the derivative of the exponential function and copy the brackets as it is, then plus. Copy the first function. Now take the derivative of the brackets, but then apply also chain rule. So you have to just take the derivative of cosine first, which gives you negative a sine omega n times square root of 1 minus theta squared, then peel out the function and just look at the inside function. So take the derivative of the inside with respect to time. That's why we have this coefficient here. And repeat the same procedure for the next part. So from here, then you plug in 0 for time. E to the 0 will be 1. Sine is 0. That term will be entirely cancelled out. And you will only have this part, plus you will only have this a term here. Multiplied by this is negative zeta times omega n. So the initial velocity will be equal to negative zeta omega n, a plus b times omega n square root of 1 minus zeta squared. We already know that damped frequency is omega n times square root of 1 minus zeta squared. We already know that a is the position. So from here, b will be equal to this ratio. And then plug that back into the equation, you will get to the solution for underdamped systems. If zeta is equal to 1, then you will have a critically damped system. Then it means both of the roots will be at negative zeta times omega n, and that will be the solution. Knowing the initial conditions as this initial position and the initial velocity, using this equation with the known parameters, because t is equal to 0, you will have c1 because t is equal to 0. That term will be cancelled out. C1 will be equal to the initial position. Then take the derivative with respect to time by applying product rule. So you have the derivative of the function and plug in 0 for time. That gives you this term plus C2, because t is as a product, so that term will be cancelled out. So here is the initial velocity. And if you rewrite the equations, you will get to the solution as in this bubbled equation. And the third one, when zeta is greater than 1. So here, if zeta is greater than 1, you have overdamped system. And here will be the solution. This will be your solution. But we don't know the coefficients C1 and C2. Initial position, when t is equal to 0, should be C1 plus C2. Take the derivative and then plug in 0 for time. Then C1 plus C2 will be equal to, from here, x0. This is one equation. And here is the second equation. If you solve two equations with two unknowns, C1 and C2, you will get to this form. To be honest, I use MATLAB to symbolic toolbox to find these equations. But if you want to see them all together, and there is also a more generic form, I was able to just summarize the topic all in one page. So here are the three equations that we need if the system is underdamped, critically damped, and overdamped.